So we're going to finish up looking at our graphs, looking at the 6 basic trig graphs today. We've done sine and cosine with a lot of detail, and now we're going to look at the other 4, tangent, cotangent, secant, and cosecant. So what we're going to do to figure out what tangent looks like is we're going to rewrite tangent using trig functions that we've already studied quite a bit. So when you rewrite tangent, you can write it as a fraction, and we did this in the homework. How can tangent be written as a fraction of 2 other trig functions? Yep.
Sine over cosine.
Right. We can do sine divided by cosine. Now let's think a little bit about sine and cosine, and that's going to give us an idea of what's going to happen with tangent. All right. So let's make the graph of sine. So sine, I'm not going to put equals. Let's just do something like that. Okay, just a rough sketch. Okay. Those are my 5 points. 0, pi over 2, pi, 3 pi over 2, 2 pi. And for cosine, it's a little different. It starts up at the top, then comes down, and goes back. All right. So the first thing we want to notice is tangent is a fraction of sine over cosine. Whenever you have a fraction and there is a variable in the bottom, which there is, we need to be careful that something doesn't happen. What do we need to make sure that we avoid in the denominator of any fraction? Yeah?
Zeros.
Right. We don't want to end up with a 0. If we do end up with a 0, what does that usually mean happens when you try to graph something? If there's a spot where you could divide by 0, you get a what?
Either a break, hole, or asymptote.
Right. You can get some kind of break, hole, or asymptote. In this case, it will be an asymptote. So right away, that tells you something about tangent. If the bottom can ever be 0, meaning does cosine ever cross the x-axis? If it does, then we are going to have vertical asymptotes, which means the graph of tangent is not connected. So when you draw it, you do have to lift your pencil as you go. Okay, so let's look at cosine. Does the graph of cosine ever cross the x-axis? Yeah, where does it cross?
What?
So what's the x value for where cosine crosses the x-axis? Yeah?
Pi over 2 and 3 pi over 2.
Yeah, pi over 2 and 3 pi over 2. So if you try to plug in pi over 2 into the tangent function, let's just plug it in and see what happens on the calculator. Tangent of pi divided by 2. It can't do it. And it can't do it because you're trying to divide by 0. Right. Pi over 2, 3 pi over 2. What would be the next one?
5 pi over 2.
5 pi over 2. Every odd multiple of pi over 2 is not going to be something you can plug into tangent. Okay? You're going to get vertical asymptotes. Now, let's think about the top. I want to know when tangent would cross the x-axis. The only way tangent can cross the x-axis is if this fraction comes out to 0. How do you make a fraction come out to 0? Yeah?
The top has to be equal to 0, meaning sine has to be equal to 0 in this case.
Right. So to make a fraction 0, you need to make the top 0. To make the top 0 there, sine has to be 0. Does the graph of sine ever cross the x-axis? What do you think? Yep.
At 0, pi, 2 pi.
Yep. So every 0, pi, 2 pi, yeah, you see every multiple of pi, integer multiple, 3 pi, 4 pi, 5 pi. Every number like that is going to be where the top comes out to 0, which is going to make the graph of tangent come out to 0. In other words, those are my x-intercepts. So tangent has x-intercepts, or it's 0, whenever the sine is 0. And there are going to be vertical asymptotes in the tangent function whenever the cosine is 0. So using that, we can draw some asymptotes. We know where it crosses the x-axis, and we can use the calculator to check what happens near the asymptote. Okay, we've done that before. Like if you have an asymptote at 2, we plug in like 1.999 and see what's happening. All right, so let's see if we can make a sketch. So I wrote down some of the asymptotes for tangent. It's every odd multiple of pi over 2. So we got pi over 2, 3 pi over 2, 5 pi over. I'm not going to draw them all, because basically once I draw what's happening in one section of the asymptotes, you can copy and paste that over and over. Okay. But any question why I put those asymptotes where I did? Those are all the places where cosine crosses the x-axis. And that causes us to divide by 0. All right, so now we said that the tangent is going to cross the x-axis whenever sine is 0. Well, one place where sine is 0 is right there, at pi. So I know the graph of tangent is going to go right through that point. It's also going to cross again at 2 pi. So the graph of tangent is going to go through that point. All right, so now let's pick a value very close to pi over 2 and plug it in for tangent. Okay. To get something close to pi over 2, I would just go like this. Plug in, let's go pi divided by 2. And do I want a number a little bigger than pi over 2 or a little smaller if I want to check what's happening to the right of asymptote number 1? Yeah.
Smaller.
So smaller would bring me that way, right? That would bring me to the left of the asymptote. So I want to try a number that's bigger, right? I want to go a little bit bigger because I'm trying to stay in between, we'll call that asymptote 1 and asymptote 2. So what I'm going to do is just go a little bit bigger, like that. So I'm going to do the tangent of pi over 2, and I'm going to add a really small amount to it. What's happening to my y value when I'm very close to pi over 2, but on the right side of it? What's my y value? Yes, what's my y value approaching? So look at what we plugged in and the result that we got.
Is it 1,000 or negative 1,000?
No, not negative 1,000. What am I approaching? No. Yeah.
Negative infinity.
Negative infinity, right? It's heading down forever. Okay, so that point, I'm just going to represent that as negative infinity. That's as low as I can go. Now, we still want to stay between asymptotes 1 and 2, but I want to check what's happening to the left of asymptote 2. So would that be a number a little smaller or bigger than 3 pi over 2? Yep.
Slightly smaller.
Slightly smaller. So let's see what happens if we do the tangent of 3 pi over 2 and just make it slightly smaller. Okay. What's happening to my y value as I approach asymptote 2? Yep. It's approaching infinity. Okay. So let's pretend that's at infinity. It's as high as I can go. So now I need to connect these 3 dots. And they're going to be connected in kind of like a curve. So we have to stay, what I'm going to do is I'm just going to make that, it's easier if it's smaller for me to draw it like that. Okay, I have to stay very close to the asymptote, like that. But I can't continue to stay close because I have to go through that dot in the middle. So at some point, I need to start to curve. And then I want to keep curving, but I can't because I'm running into another asymptote. So I need to get up as close as I can to it, but not cross it. Basically like that. And if you copy and paste that, that is what your graph of tangent looks like. And I can show you on the calculator as well. So it's these repeating sections that have that curve to them. And the one that we drew is that one right there. It's the first cycle of the tangent function that is completely to the right of the x-axis. But that's what tangent looks like. All right. Any question on that? Now the other thing we have to kind of keep straight is how many asymptotes are there per cycle? Okay, so let's label these asymptotes. So asymptotes 1, 2, and 3. And then up here, let's call this cycle A, and that one cycle B. So cycle A is bounded by asymptotes 1 and 2. How many asymptotes do you think there are per cycle? There have to be the same number of asymptotes in every cycle. Yep?
2.
Okay, so which asymptotes, and remember, an asymptote can only belong to one cycle. Can't belong to two. So you said there's 2 asymptotes per cycle. Then what are the asymptotes in cycle A? Let's go with this for a second.
There have to be 1, so it'd be 2 pi. Or the asymptote 1 is for cycle A, and then there's only 1 per.
There's only how many?
There's only 1.
Yeah, they can only be 1, because an asymptote can only belong to one cycle. And if you said there were 2, then you could say, like, okay, asymptotes 1 and 2 belong to cycle A. So then what belongs to cycle B? You can't say 2 and 3 because 2 is already used. And you can't just say 3 because we said it had to have 2. So it doesn't make sense for it to have 2 asymptotes per cycle. It doesn't matter how you think of it, whether you think of the asymptote on the left as belonging to it or the right, as long as you understand there's just one asymptote per cycle, okay? Or per period. Now that's another question. What is the period length? Well, it's the distance between asymptotes 1 and 2, or 2 and 3. How much distance is between those 2 asymptotes? Yeah?
Pi.
Pi. So the natural cycle of tangent and cotangent is pi, not 2 pi. Okay. So tangent has a naturally shorter cycle than sine and cosine. All right, now, let's think about cotangent. Cotangent, what's the connection between tangent and cotangent? There's a name we can use to describe them. How do they compare to each other? Yeah?
They're reciprocals.
They're reciprocals. So basically, what's going to happen with cotangent? Well, everywhere that you had an asymptote in tangent is going to turn into a what in cotangent? All your asymptotes from tangent are going to turn into, yeah?
Zeros.
They're going to turn into zeros in cotangent. What's going to happen to all your zeros from tangent? Yep.
They're going to turn into asymptotes.
They're going to turn into asymptotes. So all the zeros and asymptotes are going to change places. When I think you dropped, can you pick that up for me? Thanks. So those are going to switch places, and the direction of the curve switches. Okay, it goes the other way, and we could verify that by doing what we did before. Pick a point near each asymptote and check it out. But let's just let me get rid of that page, and then you can see both at the same time. So before, pi over 2 was an asymptote. Now, pi over 2 is 0. Before, pi was a 0. Now, pi is an asymptote. Right, so that's the connection between tangent and cotangent. Curve switches direction, and all the asymptotes and roots switch. Same deal with the asymptotes. There is only one per cycle. There can't be two. That wouldn't work. And that's it. So any questions on the graph of tangent versus cotangent? Yep.
So cotangent is technically 1 over tangent.
Mhm.
Okay.
Yes. Yep. You can think of tangent as sine over cosine. You can think of cotangent as cosine over sine. It's just the flip, reciprocal. Yep. All right. So now let's look at that. So we kind of already said this, but the period of tangent and cotangent is pi. Again, look at the distance between asymptotes 1 and 2. Asymptote 1 is at 0. Asymptote 2 is at pi. They're pi apart. And because they are pi units apart, that means you can add any multiple of the period to a value, and it will not affect the tangent or cotangent. Okay. For example, take the tangent of 1.4. Okay. You get that. If you take the tangent of 1.4 and you add pi to it, it's exactly the same thing. What you're doing is you're just taking the answer that you had. Let's say your answer was right about there, and you're repeating that answer in the same, it's in the same y value position. It's just one cycle later. That's what I did right there. Right? If you take that same value and you look at it 2 cycles later, it's going to be at exactly the same y value again, just 2 cycles later. You could also looking at cycles before. If you minus pi, you're getting the same answer, but this time you're going back a cycle. Right? So adding any multiple of pi to a value does not affect the tangent or the cotangent. Now, if you add something other than a multiple of pi, let's say you add like 1.5 pi, you can't do that. You can't add half a cycle and get to the same spot. You either add a full cycle or you subtract a full cycle. Okay. Any question on that idea? When we did it for sine and cosine, what did we have in that spot that I just circled? You can't add pi. Right? If you take like 0.25, you take 0.25 and you add pi, that didn't quite work. Right? When you add pi, it didn't give me back the same answer. What was it for sine and cosine? Yep.
You subtract it from pi? Or you subtract the previous answer from pi?
No, it's a different number in that red circle. Something you can add and subtract and get the same answer with sine and cosine. Well, it's an integer times something, but it's not pi. What was it for sine and cosine? Yep.
Was it pi over 2
No.
for cosine or sine?
No, it wasn't pi over 2. Where is this pi? Where is this coming from? That pi that I put there is the what? Yeah. It's the period. Yeah. The period of the tangent and the cotangent function. So what would it be for sine and cosine? Yep.
Period minus.
Okay, can you be more specific?
N is period minus.
Well, n is just an integer. Represents how many cycles earlier or later you're looking at. The number you multiply by n, that's what I want to know. Yep.
2 pi.
2 pi. Yeah. So when you do this formula with sine and cosine, you can add 2 pi to any number, and you will still get the same answer one cycle earlier, later, 2 cycles, however many cycles you want to look at, earlier or later. All right, so now let's look at transformations. Okay, by now we got to know these transformations. They've been the same for pretty much the whole year. So I'm not going to go through in detail what each one of them does, but I do have the chart up there you can take a look at and copy down if you need it. Okay, so transformations work exactly the same. Does anyone have any general questions about transformations? There's nothing different.
What's the phase shift?
What's a phase shift? We don't call it that normally with the other transformations, but in trig we do. Yep.
Phase shift is, in a way, it's just a fancy term for a horizontal shift, to my understanding.
Yeah. And I'm going to call it, I'm not going to call it amplitude with tangent. I'm going to call it a vertical stretch. I've never heard of tangent really having an amplitude because it goes up and down forever. So usually amplitude refers to a function that is bounded. It doesn't go up and down forever. So we'll just call C the vertical stretch. So vertical stretch, period change, phase shift, vertical shift. And now when you were finding the period for sine and cosine, what was the formula that we used? It was a fraction. Yep. 2 pi over b. What do you think the formula to find the period for tangent and cotangent is going to be? Yep. Oh, yeah. Pi over b. Yep. It's the original period divided by b. Okay. Every trig function that we've studied pretty much is going to have a cycle length of 2 pi. The only ones that don't are tangent and cotangent. All right. So that was the next thing. To find the period of tangent or cotangent, the formula is pi over b. All right, now I'm going to skip what's next because I think it'll make more sense if I do something else and then come back to it. But one thing that we want to be able to do is if I give you a trig function, I want you to be able to make a list of all the asymptotes, okay? Especially if you do a transformation. If you don't do a transformation, well, you've got the asymptotes right there for cotangent, and you've got them right there for tangent. Okay, so we're gonna come back to how you find the asymptotes for any trig function in a little bit. Okay, so I'll come back to that. All right, let's try an example with tangent. So it says find the period, and then find a viewing rectangle that shows 3 full cycles. So let's start with the period. What's the period of tangent 2x? Yep.
Half pi.
Yeah. Pi over b, which is pi over 2. Now they're asking me to show 3 full cycles. How long are 3 cycles going to be? Yeah. 3 pi would be 6 cycles. Yep.
3 pi over 2.
3 pi over 2, yeah. So we need to set a window that's 3 pi over 2 units wide. You can do that however you want, as long as the difference between your x min and your x max is 3 pi over 2. I usually just go 0 to 3 pi over 2. By always sticking with 0, that means I may break a cycle into a half. Okay, I may cut a cycle off. But as long as I show 3 full cycles, it's okay if you break one up. Let's hit graph. Right, and I did. That's a half cycle. Let's see. Did I not put 3 pi over 2? Or maybe I didn't type in tangent 2x yet. Okay. sure you type in the actual problem. All right, so that's a half cycle. Okay, that's a full cycle. That's another full cycle. And I'm ending with a half cycle. So I have two halves, which makes a whole, and then the two in the middle. So that's technically 3 cycles. If you wanted to show those connected without showing 4 separate pieces, you could adjust your window by the right amount to make it start at a nice spot. I'm not worried about adjusting that. Any question how I got the 3 cycles there? All right. Let's try this one. It says, using the graphs below, one of them is the graph of 2 tangent x, one of them is 5 tangent x. I just want to know which one is which. Anybody think they know which one is the 2 tangent x? Yeah.
The one on the left.
Okay, how come?
It looks like more.
It looks like a 2, huh? Looks like a 2 tangent.
Well,
Just it's exuding 2 tangentness.
yeah.
So let's take something like this. Okay, so there's your graph of tangent. And if I zoom out a lot here. If I take that and I stretch it vertically, okay, watch what happens to it. That's what happens when you stretch it. And that's what happens when you compress it. So anybody have any thoughts on that? Yeah?
Left is 5 tangent, right is 2 tangent, because 5 tangent is more stretched out, looks skinnier.
Yeah, the more you stretch it, the less apparent that curve starts to become. Versus when I compress it, now you can really see the curve more. So looking at those 2 graphs, I would say the one on the left is starting to look like it's been straightened out a little bit, and that's because it's been stretched more. So this one is, let's see, that's the 5 tangent x, and this one is the 2 tangent x. Okay? So you'll probably have a question kind of like that on the test, where you have to identify a graph based on a picture. Okay? Any questions on that one? Yeah.
Will it always be a whole number before the tangent?
No, it doesn't have to be. You could stretch by a fraction or decimal amount. But I wouldn't give you the graph of like 6 tangent x and 7 tangent x. You probably wouldn't be able to tell. I would have to make them distinct enough that you can really see the transformation. With a 2 and a 5, you can tell relatively obvious. I mean, in terms of they look different.
It just mostly depends on the zoomed in.
Yeah, but I would give you graphs that definitely look significant enough difference. All right, so now let's start to think a little bit about secant and cosecant. Let's start with cosecant. How can we write cosecant as a fraction? And we have to do this every time we plug in a cosecant value because you don't have a cosecant button on the calculator. Yeah?
It's 1 over sine.
Yep, 1 over sine. And how can we write secant? In other words, if I asked you to find the secant of 3 degrees, how would you type that in on a calculator?
1 over cosine.
1 over cosine. When we think of those 2 functions the way we've just written them, it gives us a little bit of insight into what could happen when you start to draw secant and cosecant. looking at these two things, does anybody notice what could happen when you draw secant and cosecant? Yep. There could be asymptotes. Cosecant is going to have an asymptote everywhere that the sine crosses the x-axis. 0, pi, 2 pi. Secant is going to have an asymptote everywhere that cosine crosses the x-axis. Pi over 2, 3 pi over 2, 5 pi over 2. All right, so let's look at cosecant first and see if there are asymptotes at every integer multiple of pi. Here's cosecant. And the asymptotes, I just kind of wrote them down for you, but it's every integer multiple of pi. For secant, it's the ones that are odd multiples of pi over 2. And we could figure out kind of the U shape and the N shape by plotting, bless you,
Thank you.
by putting in some points on the calculator and checking it. But I don't want to go into that much depth with these two graphs. So first, we need to kind of understand what is a full cycle. All right. Well, let me label my asymptotes. From asymptote 1 to 3, that is a full cycle. When you are drawing secant or cosecant, you need to have one full U shape and one full N shape. That's a full cycle. So now, another way you can think of it is sections A and B together make up one full cycle. So if you look at one full cycle, which is basically the part that I just bracketed, how many asymptotes are there per cycle? So out of asymptotes 1, 2, and 3, which ones belong to the sections between A and B? Yep.
1 and 2.
Yeah, there's only 2 asymptotes per cycle. So we could say that asymptotes 1 and 2 belong to the first cycle. 3 and 4 belong to the next cycle, which I kind of cut off, but it would be over here like this. And same deal with secant. Asymptotes, label these. You could say that asymptotes 1 and 2 belong to a cycle, and then asymptotes, well, it would be 3 and 4 belong to the next cycle. But there's only 2 per cycle. And the key to figuring out where the new asymptotes are is you need to know where the original asymptotes are. As long as you know that, you can do any kind of transformation you want and figure out where the new ones are going to be. And that's what I'm going to give you a chart for. So I'm going to give you a chart that breaks down tangent, cotangent, secant, cosecant, where the original asymptotes are, and then how you find the new ones. How you find the new ones, I kind of started to show you right here. Okay, so I'm going to come back to that in a second. But first, let me give you a summary of all the asymptotes for the original trig functions. That's what's in the left column. So tangent, the first positive asymptote is at pi over 2. Cotangent, well, we'll call it the first non-negative asymptote, is at 0. For secant, your first 2 positive asymptotes are pi over 2 and 3 pi over 2. And for cosecant, your first 2 not negative asymptotes are 0 and pi. Okay, what I need to explain is this column. And that's what the directions back on the other page are going to show you. So all these ones that I just highlighted in green, those we have to calculate. Those are what we call the new, it's basically where the original asymptote moved to. So when you describe the new asymptotes, first thing you have to do is describe to me where did the two original asymptotes move to when you do a transformation. Then, once you describe those, explain to me that those asymptotes are going to repeat every cycle. That's what the period times n part is. So when you put period times, it doesn't have to be n, it could be any letter. But this part on the end is describing the fact that it's going to repeat forever. That's what that part does. And that's the easiest way to describe asymptotes. Just find one or two of them, and then tell me that those repeat forever. With tangent and cotangent, you only have to find one, because there's only one per cycle. With secant and cosecant, you do have to find two, because there's two per cycle. Okay, and once people copy that down, I'm going to go back to the other page, which is going to describe how do you figure out the part that I highlighted in green. Does everybody have that chart? You really just need the left side. The right side, it's kind of all the same every time. All right, so how do you figure out your new asymptotes? Well, the first thing is you need to know the original asymptotes. How are you going to know that? I just gave you a chart. So find all the asymptotes in the original function for one cycle. Okay, just look it up in your chart. Now, if you do something like this, let's say tangent of 3x. The asymptotes might not be in the same spot. We have to figure out where the asymptote in that chart is going to move to. To figure that out, take the asymptote from the chart, the original asymptote, and set it equal to what's inside the parentheses. That's going to tell you where that one asymptote moves to. Okay. Does it describe all the asymptotes? No. It's describing where that one asymptote shifted to. Once you figure out where it moves to, in step 2, you're going to tell me that it repeats forever. And the way you describe it repeating forever is you put plus period times n. Period times n is saying that you can add any integer multiple of the period to the asymptote, and you will get a new asymptote in a later cycle or an earlier cycle. So that number that you put right there, that's what you're getting in step 2. And that number that I just circled in red, that is the number that is highlighted in green. So now you know how to find what's highlighted in green. Okay, so now they're going to ask us the same kind of things they always do. I'll give you like a tangent or cotangent or secant, and I'll say find the domain, range, period, and asymptotes. We didn't have asymptotes with sine and cosine. Now we do. Okay, does anybody have those two steps? Let's try this out. So this one doesn't even have any transformations. It just says find the domain, range, period, and asymptotes of the regular secant function. Let's start with the period. So I don't know if I had scrolled down enough for you to see this earlier. I think I mentioned it, that the formula to find the period length is the original cycle divided by b, and tangent and cotangent are the only two that have a cycle of pi. Secant, cosecant, sine, and cosine are all 2 pi. And if b was ever negative, you don't, technically that's why sometimes you'll see absolute values around the b, because the period is a measurement of length. You wouldn't have a negative period. All right, so let's go back to our example and find the period. Period for secant is 2 pi over b. What's b in this case? 1. So it's just going to be 2 pi. That's the easy one. Period is 2 pi. The range, let's think about that. So we're going to look at secant, and actually cosecant would be the same range. Does secant go up forever? Yeah?
Yes.
Okay. Does it go down forever?
Yes.
All right, so negative infinity and infinity are going to be involved in the range. Does it hit everything in the middle? No, there's a gap. There is a gap right in there. It never hits anything in that gap. So what does it look like that gap is? It's between, yep. The gap is between -1 and 1. So how would you describe the range of, let's start with this lower part. The lowest it goes, up to the highest it goes, just the lower part. Yep.
Negative infinity to negative 1.
Okay, so we go from negative infinity up to and including -1. And now how would you describe the range of the upper part? Yep.
1, 2, and including, or 1, or including 1 and 2 infinity.
So that's how you describe the range. Ranges of secants and cosecants always need to be described with a union, because they're 2 separate pieces. Okay, let's do the asymptotes. Okay, we're doing secant. What are my 2 original asymptotes that I gave you in the table for secant? Yep.
Pi over 2 and 3 pi over 2.
Okay, pi over 2 and 3 pi over 2. And it says to take each of those arguments, set them equal to the argument, and solve. What's the argument in my function? What is it?
Or secant of x, or is that?
That's not the argument, that's the function and the argument. What's just the argument?
Oh, f. So would that be x?
X. X is, no, not f of x. F of x is your independent. X is your argument. So in this case, we're going to set the original asymptotes equal to x and solve. Well, if we do that, x equals pi over 2. Oops, don't write them under domain though. X equals pi over 2. X equals 3 pi over 2. And now solve for x. Well, there's no transformation, so there's nothing to solve for in this step. Now, you have not described all the asymptotes. You've described 2 of them. How often are each of those asymptotes going to repeat?
Every 2 pi.
They're going to repeat every 2 pi units. So what could I put on this top one? to represent that it repeats every 2 pi units forever, both forward and backwards in cycles. Yep.
Plus or minus period 2 pi.
Plus, what are we going to put in this box?
Period of 2 pi.
And how would you write that?
Word period. That's how we would for period of n.
Like literally write that word, you can't write a word out though.
And and 2 pi?
You can't on the graphing calculator.
So what would you say?
N 2 pi?
Yeah, or 2 pi n. That represents that asymptote repeating. You can add 2 pi to that number, 4 pi, 6 pi, 8 pi, 10 pi. And because n can be a negative number, that takes care of subtracting as well. What would you put on the bottom one? Yep.
And also 2 pi n.
Yes. Bless you. Now, if you're thinking, well, is there a way you could actually combine those two together? You could. If this one is repeating every 2 pi and that one is repeating every 2 pi, there's probably a simpler way to describe all of these answers together, which I'm not really going to get into too much, but yeah.
I think you can just remove the 2 and that will take care of both. In 2 pi n.
Yeah, you could, so like this top one, this is pi over 2, and if you add 2 pi n to it, you're adding 4 pi over 2. I'm just adding 2 pi one time. That gives you 5 pi over 2. So the kind of asymptotes that are going to be generated from the top one are pi over 2, 5 pi over 2. The next one would be 9 pi over 2. And the one after that, 13 pi over 2. That's the asymptotes the top formula gives you. And it keeps going. The bottom formula is going to give you asymptotes like 3 pi over 2, 7 pi over 2, 11 pi over 2. If you put them all together, you're getting asymptotes at all the odd numbers. The top formula is giving you some of the odds. The bottom formula is giving you the rest of the odds. Putting them together, you get all the odds. So I'm not worried about trying to combine these two into one formula. You can, but if we write it like that, that's okay. And now the domain, the way we usually write that, is it's every x value that's not an asymptote. Okay, that's how I write it. All reals except the asymptotes. And that's how you find all 4 things. Now, if we did that for cosecant, would the range be different? Look back at your graph. Is the range different between secant and cosecant?
No.
No, it has the same gap. So there would be no change in the range. Would the period be different?
Yes. No.
No. Period is still 2 pi over b, and there's no transformation there, so the period would stay the same. What would change is the asymptotes. Instead of a pi over 2 and a 3 pi over 2, what numbers would you put in those 2 spots if you were doing cosecant?
0 and pi.
You would put 0 and pi. Yep. That's the only thing that would change on that problem. Okay. All right, let's try this one. So find the period and the asymptotes and show a complete graph. Okay. Cosecant. Is it 2 pi over b or pi over b? Which formula do we use? 2 pi over b. What's b in this case? 3. So there's our period. You always want to find that first because you're going to need that. Okay, now, find the asymptotes. Where are the two original asymptotes for cosecant? Yep.
0 and pi.
The two original asymptotes are 0 and pi. We're going to set each one of those equal to what? And solve. Yeah.
X.
In general, what do we set them equal to?
The argument.
The argument. What's the argument in this case?
3x.
3x. So set each asymptote equal to the argument and solve. Now remember, what should happen, that's a big number, it should compress everything smaller. In this one, we still get x equals 0, because if you have an asymptote on the y-axis and you compress it towards the y-axis, well, it's already on the y-axis, you can't squish it towards it. But the asymptote that was at pi, where is that asymptote going to end up?
Pi over 3.
Right, it's going to be compressed towards the origin by a factor of 3. So those are my two new asymptotes. Now we have to put how often they repeat. What would I put on the end of the first asymptote to indicate that it repeats forever?
Would it be n 2 pi over 3?
Yeah, you can add any multiple of the period to that number, and you will get that asymptote in a later or earlier cycle. And yes, technically you don't need the 0 there because adding 0 to that doesn't change anything, but if you write it that way, that's fine. And how about my second asymptote? Yeah.
Pi over 3 plus 2 pi over 3n.
Yep. You can add any multiple of 2 pi over 3 to the original, and you'll get a new one. Yep. And again, you could combine these if you wanted to, like we did earlier, but it's okay if you leave them separate. The book combines them, so when I read the answers for homework, if you don't combine them, which I'm not asking you to, we'll just have to do those out by hand because I'm showing you a different way to do it. All right. Any questions on that? All right.
You had to show a complete graph too.
Oh yeah, show a complete graph. All right, so it says to show 2 cycles. So that's going to be 4 pi over 3. That should be 2 full U shapes and 2 full N shapes. So to type that in, you have to type it like that. That's the cosecant of 3x. And we got to set our window to be 2 cycles wide. So let's go 4 pi divided by 3. And it'll change it to a decimal for me. All right, so let's see if we get 2 U shapes and 2 N shapes. So that's a half cycle. That's a full cycle. That's 1.5 cycles, and that's 2 cycles. Perfect. So there's your complete graph. All right, so now let's apply that same idea to finding a solution that we just did to an asymptote. If you can find one solution to a trig equation, then that solution is going to repeat forever. Yesterday, we did not write the answer that way. I gave you a window, and I said find all the answers between 0 and 2 pi. Well, today, I'm going to have you find all the solutions in one cycle, and then you're going to just tell me that those answers are going to repeat. How often do they repeat? Every period times n. I can't fill in period because I don't, depends on the problem. find all the solutions in one cycle, just like we did yesterday, that part's the same, but then put plus period times n on them. That's the only difference. And that'll represent every solution. I think that was the last one. Yeah. All right, so it says to find all solutions to cosecant x equals negative 1.6. Well, first you have to know how to type that in. 1 divided by sine. We're going to put negative 1.6. And what's the period of cosecant? Yep.
2 pi.
2 pi. If you don't set your window to one cycle, you're going to confuse yourself. You're going to see more information or not enough. You want to set it to one cycle. And I usually go 0 to the number. Okay, so make our graph. Oh, that's doing that. I know it's going to cross twice. We're going to do second calc intersect. Get the first answer, 3.82. And the second answer, that's going to be 5.61. And if that's all you write, you have not done all solutions. You've done 2. What would I put on the end of that one that would give me a formula to calculate later or earlier answers? Yep.
Plus 2 pi n.
Yep. And again, understand n is an integer. And same thing here. That is how you represent all solutions. You've got to put the plus period times n. And that's the last one we're going to do. Okay. So that finishes up graphic. All right, so that's the homework on page 352. Take a look at that first thing tomorrow, and then we'll do section 6.5, which that's the last section for this week. I'm just going to split 6.5 into 2 days.